We now move on to the last part of probability, which is the conditional probability. What that means is that it's a probability of a second event happening given the first event has already happened. So, for example, suppose we have this. What is the probability of selecting the letter E from the word ACE, ACE? E is one out of the three letters, therefore the probability of you selecting the letter E from that is just 1 over 3. Obviously, we are considering that choosing each letter has an equal probability. Okay? Then we go to the conditional probability part. What is the probability of selecting the letter E? Same thing, given that a vowel is selected. So, if we have ACE, we are already told a vowel is selected, meaning it's one of these. And then we are told that we chose this from that. So, total possible outcomes now is not all of them, it's the one that you are given. So, the vowels, so 2. Therefore, this then becomes just 1 over 2. Because you're choosing E out of a possibility of 2 options since we know, or since we're given that a vowel is selected. And remember, this terminology is very important. The probability of A given B, so event A happening given B has happened, is written like this with this vertical line. Let's look at a few examples. A child is selected at random from a group of 11 boys and 9 girls, and one of the girls is called Rose. Find the probability that Rose is selected given that a girl is selected. So now the total outcomes is not 20, it is just 9, because we are told that a girl is selected. This event has already occurred. So the total possible outcomes is 9. And from that, what's the total successful outcomes? It's just Rose being selected, so that one particular girl. So that's going to be the probability that Rose is selected given that a girl is selected. Conditional probability, where the condition is that the girl is selected. Next, the following table shows the number of students in a class who study biology and who study chemistry. Represent the data in a suitable Venn diagram and find the probability that the randomly selected student studies chemistry given that they study biology, and B, do not study biology given that they do not study chemistry. So first, let's just draw the Venn diagram for this. So we have our universal set, chemistry and biology, and we're given some values here, where C intersection B complement, which is only the left part of C, is 8, and then C intersection B is going to be 9. B intersection C complement, so only the right part of B, is 7. And we have B complement intersection C complement, which is just the outside, which is just 1. How do I know it's intersection? Because in a table, you're assuming both of these happen to get this number. And both of them happening is just the intersection. Now we're told, find the probability that the randomly selected student studies chemistry. So studies chemistry is this entire circle, but we are given that they study biology. So this is now your total possible outcomes because they study biology, we have already been told. And you're told to find the probability that they study chemistry, which is just this part of the biology people. Because remember, we've already given that they study biology, which means now our probability here will be 9, which is the success outcomes, divided by the total people who study biology, which is 9 plus 7, which is just 16. The second part is that find the probability that they do not study biology, given that they do not study chemistry. Because we've been given this, that is going to be our total possible outcomes. Not studying chemistry is everything outside chemistry. Then we are told that they do not study biology from there. So from whatever is already selected, from all the red, what is the one that does not study biology as well? It's just this here. Therefore, our total possible outcomes is 7 plus 1, which is 8. And our success outcome from that is just 1. Therefore, this is going to be our probability for people who do not study biology, given that they do not study chemistry as well. Next, we are told that 2 children are selected at random from a group of 5 boys and 7 girls. Find the probability that the second child selected is a boy, given that the first child selected is A, a boy, and B, a girl. So we can do that using our tree diagram, where our first choice will either be a boy or a girl, From that, then we're going to have the second choice being either, again, a boy or a girl, and a second choice for the girl being also a boy or a girl. Let's write down our probabilities first. We have 12 children in total, 7 plus 5. From that, 5 are boys. So initially, the probability of you choosing a boy is 5 over 12. And the probability of you choosing a girl is 7 over 12. Then, because they've already been selected, the number of students goes down to 11. And to choose a boy after originally a boy has already been chosen is going to be now 4 over 11. This is going to be 7 over 11. This is going to be 5 over 11. This is going to be 6 over 11. Then we are told, find the probability that the second child selected is a boy, given that the first child selected is already a boy. So if we are already given this, we don't have to go through this first stage. We are already at this stage here. Now we are told, find the probability that the second child selected is a boy. And so the total possible outcomes is this and this together, which obviously adds up to 1. From that, to get a boy is just 4 over 11. Therefore, the answer here, find the probability that the second child selected is a boy, given that the first child is a boy, is just going to be 4 over 11. We do a similar thing for the second part. We are already given that the first child is a girl. Therefore, we are not going through this stage. We are already at this stage here. Now, once we're already here, what's the probability that the second child is a boy? The probability there will be 5 over 11. So that's going to be our answer here. Then we go on to the conditional and dependent probability formula, where we do what we've already done before, but now we have it in notation, where the probability of event A happening given event B has already happened is the same as the probability of both events happening divided by the probability of the given event happening. Because now this is going to be your total outcomes that are there. Then obviously you can change this after cross multiplying into this right here. This formula is when you have dependent events like the previous one, where you selected a boy. Now that boy is not available for selection, so your probability changes. If you have independence, remember what happens when you have independence? The probability of A intersection B is just the same as the probability of A multiplied by the probability of B. That's the condition when you have independent probabilities, two independent events. And so what you can do is change these things right here, where the probability of A given B will be equal to the probability of A intersection B divided by the probability of B. Then the top here, you can just write it as probability of A times probability of B. And then what happens? You can just cancel these two out. It leaves you with the probability of A. So if A and B are independent, then the probability of A given B is just equal to the probability of A. If the condition is if they're independent. Now we're told 2 children are randomly selected from 11 boys and 14 girls. Find the probability that the selection consists of 2 boys. So you having 2 boys being selected means the first one has to be a boy. So the first selection has to be a boy, meaning you have 11 out of a 25 probability of that boy being selected the first time. Then the second time the boy gets selected, remember, the number of boys have gone down to 10. The number of total students has gone down to 24. So times 10 over 24. What this ends up giving you after simplifying is 11 over 60. That's the probability that 2 boys are selected out of the selection of 2 children. Next, what if you wanted a boy and a girl in any order? So you have either a boy then a girl, or you have either a girl then a boy. To get a boy then a girl, you have to find the probability of you selecting a boy at first, multiplied by the probability of you selecting a girl second. That happens how? Probability of you selecting a boy first is 11 over 25, because there are 11 boys out of 25 children. Now the children have gone down to 24, but the girls have still remained 14. So that's going to be it for choosing a boy then a girl. Similarly, for a girl then a boy, you have 14 out of 25 initially. Then you have 11 out of 24 because 1 child is taken. What this gives you after simplifying is 77 over 300. Same here, 77 over 300. And because it can be either or, what you have to do is add these two occurrences. So we end up getting 77 over 150. That's going to be the probability that a boy and a girl are selected when two children are selected. Next, every Saturday, a man invites his sister to a theater or to the cinema. 70% of his invitations are to the theater, and 90% of these are accepted. His sister rejects 40% of the invitations to the cinema. How are you going to do this? Using a tree diagram. So firstly, the boy invites his sister to either the theater or the cinema. Then each of those invitations can either be accepted or rejected for the cinema as well. Accepted or rejected. The probability of him inviting to the theater is 0.7. And the probability of him obviously inviting to the cinema is a complement of that, which is just 0.3. Because I have to add up to 1. Then the probability that the theater invitation gets accepted is 0.9. And obviously rejected is going to be the complement of that, so 0.1. The probability that the cinema invitation gets rejected is 0.4. And obviously the complement of that, so that it being accepted, is 0.6. Now we have drawn our tree diagram. They are then told to find the probability that the brother's invitation is accepted on any particular Saturday. Any type of acceptance. So there are two types of acceptances here. One is the theater acceptance, and the other one is the cinema acceptance. We have to find the probability of these two combined. The probability of him getting accepted for the theater is going to be 0.7 multiplied by 0.9, which is going to be 0.63. And him getting accepted for the cinema is going to be 0.3 multiplied by 0.6, which is going to give him 0.18. So the probability of him getting accepted in total is going to be the addition of the two, because these are both events and it can be either or. When you add these two, you end up getting 0.81. That is going to be the probability that his invitation is accepted generally, whether it's a theater invitation or a cinema invitation. These are the final three examples. Given that the probability of A intersection B is 0.36, the probability of B alone is 0.9, find the probability of A given B. Remember, probability of A given B is just equals the probability of A intersection B divided by the probability of B. And that is quite direct, where we just have 0.36 divided by 0.9, which just gives you 0.4. That's going to be the probability of A given B in this question. Next, we're told that an ordinary fair die is rolled, which is a die from 1, 2, 3, 4, 5, up to 6. Find the probability that the number obtained is prime given that it's odd. So we already know that the number is odd. 1, 2, 3. 3 possibilities for it being odd. What's the probability of it being prime now from these 3 numbers? This is a prime number, this is a prime number. So 2 out of those 3 are going to be prime, and therefore that's the probability that the number is prime given that it's already odd. Because now the total outcomes is the odd ones and the success ones are the prime ones. Then we're told a boy walks to school 60% of the time and cycles 40% of the time. He is late to school on 5% of the occasions that he walks, and he is late on 2% of the occasions that he cycles. Given that he is late to school, find the probability that he cycles. So for that, we can first start off by visualizing what's happening with a tree diagram. So we either have walking or we have cycling. Then for each of them, there is either a late or a no late. Cycling as well, late, and a no late. We're going to fill this with the probability. So he walks 60% of the time, so 0.6 is his probability, and he cycles 0.4, 40% of the time. He's late to school 5% of the time when he walks, so 0.05, and not late for the other time, so 0.95. And he's late when he cycles 0.02%, and he's not late 0.98. Now they are saying given that he's late to school. What are the options that he's late? This one here, and this one here. So that's our total possible outcomes. The probability of the total possible outcomes is 0.6 times 0.05, and here it is 0.4 times 0.02. This gives us 0.008, and this gives us 0.03. Then we're told, find the probability that he cycles. That is, find this right here. So remember, even with the formula, we have probability of C given L is equal to the probability of C intersection L divided by the probability of him getting late alone. The probability of him cycling and being late is this here, which is 0.008. And the probability of him being late generally is these two options. So 0.03 plus 0.008, which gives you 0.008 divided by 0.038. And that's going to be the probability. We can simplify it, and that will give us 4/19. That is going to be the probability that he cycles given that he's late to school.